Thermal analysis, polymer, മാത്രമല്ല every ഇപ്പൊ ഒരു ലിസ്റ്റ് കാണാൻ പറ്റും. ഒരു വളരെ വലിയ ലിസ്റ്റ് ആണ് അതിന്റെ ആപ്ലിക്കേഷൻ ഏരിയ തെർമൽ.
ഞാൻ ചെയ്തിരുന്ന പ്രോട്ടീനിലാണ്. ഞാനും DSC ചെയ്തിട്ടുണ്ട്.
DSC ചെയ്തിട്ടുണ്ട്. ഓക്കെ. ഏത് ഇൻസ്ട്രുമെന്റ് യൂസ് ചെയ്ത ഡോക്ടർ ജിഷ?
എനിക്ക് എക്സാക്ട്ലി ഓർമ്മയില്ല. 10 years ബിഫോർ ആണ്. ഇൻസ്ട്രുമെന്റ് പേര് ഓർമ്മയില്ല. ഐ തിങ്ക് ഷിമാട്സു അല്ല.
പെർക്ലംബർ ആയിരിക്കും. അല്ലെങ്കിൽ
ആണെന്നാണ് എന്റെ ഓർമ്മ.
അല്ലെങ്കിൽ മെറ്റ്ലർ
ആണ്.
മെറ്റ്ലർ ആവുള്ളൂ. മെറ്റ്ലർ, പെർക്ലംബർ, ഷിമാട്സു, TA ഇൻസ്ട്രുമെന്റ് ഒരു കമ്പനി ഉണ്ട്. പക്ഷെ അവരുടെ ഇൻസ്ട്രുമെന്റ്സ് വളരെ എക്സ്പെൻസീവ് ആണ്. TA ഇൻസ്ട്രുമെന്റ്സ് ഒരു അമേരിക്കൻ കമ്പനിയാണ്. പക്ഷെ വെരി വെരി എക്സ്പെൻസീവ് അവരുടെ ഇൻസ്ട്രുമെന്റ്സ്.
ഞാൻ സാറിനെ കോൺടാക്ട് ചെയ്തിട്ട് ഞാൻ ജോയിൻ ചെയ്യാം കേട്ടോ.
നോ പ്രോബ്ലം.
ഓക്കെ.
ഗിരിജൻ സാർ, ഗുഡ് ഈവനിങ്.
ഗുഡ് ഈവനിങ് സാർ. ഗുഡ് ഈവനിങ്.
സാർ നേരത്തെ ജോയിൻ ചെയ്തോ?
സോറി,
നേരത്തെ ജോയിൻ ചെയ്തോ?
ഞാനൊരു 5 മിനിറ്റായി സാർ. 5 മിനിറ്റ്.
Sir, can we start the program, Rajesh sir?
Yeah, of course.
Okay. Very good afternoon to all. Welcome to the 2-day online workshop on thermoanalytical techniques. Going to start from today onwards. Today and tomorrow, we will be covering 2 sessions. And before starting the program, I would like to mention few things. Instructions to the participants. Participants, please keep your microphone and camera muted. And you can type your queries in the chat box, and it will be addressed at the end of the session. And the feedback form will be circulated at the end of the session, and e-certificate will be provided after successful participation of the 2 sessions. With this, I would like to invite Dr. Preeti Alex, Associate Professor, Department of Chemistry, for the welcome address. Teacher, please.
Good afternoon, everybody. Today's seminar is in continuation with the workshop we conducted in August. And there we had covered JCMS, IR, UV visible, etc. Today we are going to discuss another interesting subject, that is thermoanalytical technique, which are an important methodology for material analysis. And he will be covering TGA, DTA, DSC, etc. And we are very fortunate to have Mr. R. Girijan, Consultant Product Support, Toshiba Analytical Private Limited, Mumbai. He's an expert in the field of chromatography and spectroscopy. Let me take the privilege of introducing this distinguished speaker who has joined us today. He is a product consultant in the field of analytical instrumentation with around 42 years of experience. He is a postgraduate in analytical chemistry, fellow of the Institution of Chemists, member of American Chemical Society, and life member of Indian Society of Industrial Chemistry. His experience is in pharmaceutical as well as paints and polymer field, and have approval from FDA Maharashtra in the field of chemical and instrumentation analysis. He has extensive experience in the field of chromatography and spectroscopic analysis. He is guest faculty at various institutions of national repute. He has undergone advanced training in the field of chromatography and spectroscopy at Thermo Fisher Scientific, UK, Italy, and also at Shimadzu Corporation, Japan, China, and Singapore. We are grateful to you, sir, for joining us today in this difficult COVID times. On behalf of MES KVM College, Valancheri, I extend a very warm welcome to you, sir. Next, I like to welcome our principal, Dr. C. Rajesh, to this function, and he is an expert in the field of polymer chemistry, and he will be inaugurating the function soon. Thank you very much, sir. I extend a very warm welcome to you, to Professor K.M. Rukia, HOD, who has in-depth knowledge of chemistry. I also extend warm welcome to all faculty members, students, and participants from various colleges. Please feel free to interact and clear all your doubts, because we will not have a better panel to discuss the subject. Thank you very much.
Thank you, teacher. Now I request our principal, Dr. Rajesh C., for the inaugural address.
Respected resource person of the day, Mr. Girijan, respected head of the Department of Chemistry, Professor K.M. Rukia, Dr. Preeti Alex, Dr. Jisha, Dr. Saumini, other faculty members of the department, and the participants of this workshop. So as Dr. Preeti Alex mentioned, this is a continuation of the workshop that we have organized last month about the instrumental methods for chemical analysis. In that workshop, we had deliberated on, we had a detailed discussion on GCMS, FTIR, UV, UTM, etc. And in this session, we are focusing on thermoanalytical techniques. And we have with us Mr. Girijan, a very eminent resource person who is very much capable of dealing with or handling this session. And I am very happy that it is an initiative of Mr. Girijan who called me, and he has taken an initiative to organize this kind of a workshop for our students. And at that time, I asked him that we can have this session, we can have this workshop for all the students, all the students, PhD students or MSc students from other colleges. So I am very thankful to Mr. Girijan for taking initiative to organize or taking initiative to be a part of this workshop again. And I would like to congratulate the Department of Chemistry, the head of the department, Professor K.M. Rukia, the coordinator of the program, Saumini, Dr. Saumini, Dr. Jensi, and all other faculty members for taking the or for organizing this workshop. And with these few words, I would like to declare the workshop open. Thank you.
Thank you, sir, and thank you, Dr. Preeti Alex, for the wonderful introduction you had given. I am so happy to be with you all for the second time, because the last time I came to your college was in the month of August, wherein we covered 3 different analytical techniques. One is UV visible spectrophotometry, second one was FTIR, and third one was GCMS. And today we have selected a topic, thermoanalytical techniques, which is a very, very important analytical tool in different disciplines, not only in polymer chemistry. It has got wide applications in a maximum number of industries. We will see that what are the important areas where we can have wonderful applications of thermoanalytical techniques. I mean, if you compare GCMS or UV or FTIR, in general chromatography and spectroscopy, thermoanalytical techniques tend to be a little dry topic. I mean, basically this I'm telling the students. I mean, you may feel it is a little dry topic because spectroscopy is quite interesting. Chromatography separations are quite interesting. So there we are dealing with different classes of compounds, and every analytical method has got certain limitations also, that also we had seen during our last workshop. So when we talk about thermoanalytical techniques, we are going to be concentrating on the physical properties, most of the time physical properties of material. And as I told you last time, analytical techniques can be classified broadly into three different types. One is separation mechanisms, where you have all chromatography methods coming in. Then we have identification mechanisms, where we have all spectroscopy methods. And the third category is material characterization, where you can find our thermoanalytical techniques coming in. So today and tomorrow, over this two days time, I am going to cover differential scanning calorimetry, differential thermal analyzer, and thermogrammetric analysis. So these are three topics I'm going to cover. And normally when I go for these programs, I club DT and DSC together because both are differential techniques. One is differential scanning calorimetry and one is differential thermal analyzer. Both are differential techniques. But today, I mean, there is a slight change in my presentation style, because today I am going to talk only on differential scanning calorimetry. And in the course of my discussion, I'll be slightly touching upon one of the latest development in DSC, that is called modulated DSC, which is popularly known as MDSC, modulated differential scanning calorimetry. I will not go deep into that because I will just tell you, especially for the students, I mean, you should know what is meant by modulated DSC and what are the limitations. DSC also has got, DSC is a wonderful technique, no doubt about it. Differential scanning calorimetry is a wonderful technique, but it has also got certain drawbacks. I mean, drawbacks in the sense there are certain limitations for DSC. And these limitations can be overcome when we go for MDSC, modulated differential scanning calorimetry. So I'll be briefly touching upon, I'll be showing you a few slides on MDSC, the very basic principles of modulation, and in what way modulation and modulated DSC can be of more information as compared to a normal differential scanning calorimetry. I mean, that's all my discussion will be about today. And tomorrow I'll be covering a differential thermal analyzer and also another important technique, that is thermogrammetry. Okay, with this I will go to my presentation topic. Okay, my slide is visible to everyone?
Yes, sir.
Okay, good. So let us start with thermal analysis. I have written DSC and MDSC, differential scanning calorimetry and modulated differential scanning calorimetry. Okay, so let us start with what is the definition, the basic definition of thermal analysis. Even if you refer United States Pharmacopoeia, USP has also got a definition for thermal analysis. A very simple definition is measurement of physical, chemical properties of materials as a function of time using a controlled temperature program in a specified atmosphere. Very simple definition. So we are going to have a certain measurement, certain physical and physical properties of the materials are going to be measured as a function of time against temperature under a specified atmosphere. So this is a very simple definition. Why that specified atmosphere is required is, unless otherwise mentioned, most of the time we'll be using a very inert atmosphere, that is nitrogen. Most of the time we make an experiment, we do an experiment, we carry out an experiment in nitrogen atmosphere, because in the case of thermal analysis, heating is involved. We are going to heat the sample, and the sample should not undergo decomposition or degradation under the effect of oxygen. That means it should not get oxidized unless it is required. For certain experiments, we require an oxidation. I mean, that time we are going to change the atmosphere also. We are going to see some applications where that is required. But unless mentioned, we are going to use always an inert atmosphere, and that also is nitrogen atmosphere. That is what is known as a specified atmosphere. If a different atmosphere is required, that will be specified. Other than nitrogen, if a different atmosphere is required, we can do that. We have the provision for introducing a different atmosphere into the system. So that will be as per the requirement of the method and as per the requirement of the application. Otherwise, the simple definition is, I am just repeating, measurement of physical, chemical properties of materials as a function of time using a controlled temperature program in a specified atmosphere. A very, very simple definition. And the next one, what is thermal analysis? Most students must be knowing that, because Dr. Jisha has told me that it's already there in their curriculum, in the syllabus, and most of the students must have studied about all this. So what we are trying to do is we are trying to refresh what you have already learned, what you have already studied. So it is basically a sample can be heated or it can be cooled. Both possibilities are there. Sample can get heated, sample can get also cooled. So when the sample undergoes either heating or cooling, there can be different types of changes that are possible in the system, that possible in the sample. One is there can be enthalpy change in the system. Enthalpy change, that is heat content change. There can be weight change. There can be dimensional change. I mean, I have written length change, that is dimensional change. There can be viscoelastic changes taking place. There can be decomposition with the evolution of certain gases. And there are some other changes also, which I am not mentioning, but these are the most important things. So whenever there is an enthalpy change, whenever there is a change in the total heat content of the system, it can be studied by normally by DSC. Okay, to a certain extent we can use DTA, but normally it is studied by DSC. And DT also can be used. If there is a change in the weight, mass change, normally we study this by thermogrammetry, that is TGA, thermogrammetric analyzer. We have also one more equipment called DTG, differential thermogrammetric system. I will introduce this system tomorrow when we talk about thermogrammetry. There can be changes in the dimensions. For example, change in the length. I mean, it is normally studied by TMA, thermomechanical analyzer, another important topic. There can be viscoelastic changes, which can be studied by dynamic mechanical analyzer, DMA. And if the sample undergoes a certain type of decomposition or degradation, and in the course of decomposition, if some gases are coming out, these are known as evolved gases. And then these gases also can be analyzed, and that is what is known as EGA, evolved gas analysis. For that, even we can actually connect the system to a different equipment. So that means we can make a hyphenated system. We talk about say TG-FTIR, we talk about TG-MS. So those type of systems also can be designed. So it becomes a hyphenated system wherein we can actually find out what are the gases that are coming out of the sample when it undergoes a certain type of decomposition. So these are some of the different types of changes that can take place in the sample when the sample is either heated or cooled under controlled conditions and in an inert atmosphere, in a specified atmosphere. So thermal analysis includes several different methods. Number one is DSC. I mean, that is our major topic of discussion today, differential scanning calorimetry. And we are only concerned with heat difference when we talk about DSC. Difference in the heat between a standard and a sample, a reference material and a sample, heat difference. Then DTA, differential thermal analyzer. Here we are concerned with temperature difference, again between a reference standard and a sample. So one is concerned with heat difference and the second one is concerned with temperature difference. heat difference in the case of DSC, and temperature difference in the case of DTA. Then we have TGA, thermogrammetric analysis. We are concerned with difference in mass. Either it can be difference. When I say difference, either it can be a weight loss or sometimes it can be a weight gain also. Weight can be lost and weight can be gained. So that is, but there is a change in the weight. There is a change in the mass. So we are concerned with difference in mass when we talk about TGA system, thermogrammetric analysis. Then we have TMA, thermomechanical analysis. We are concerned with deformation and dimension differences. So those are the types of changes, physical changes we study by TMA, thermomechanical analyzer. We have dilatometry, basically concerned with volume changes. We have EGA, evolved gas analysis, gaseous decomposition products. For example, if a polymeric material is decomposing, it may give out certain gases. And what are those gases? What is the composition of the gaseous mixture that is coming out of the sample? When it undergoes decomposition, it becomes an EG analysis, evolved gas analysis. And many times it is possible to measure different properties at the same time. I told you we can club two different techniques to that. So TG and DTA. TG and DTA, when I'm combining a TG with a DTA, I can get a DTA signal, I can get a TGA signal simultaneously in a single analysis of a sample. So I'm getting two different signals, two different types of information in a single analysis by combining two different methods. Similarly, I can TGA, EGA. TG, when I am analyzing a sample on a TG, when the sample undergoes, if the sample undergoes decomposition, and if it is going to give out certain gases in the course of decomposition, and these gases can be analyzed by introducing into a different, I can connect a TG to an FTIR. So I can get what are the IR spectrum of those gaseous compounds. I can connect a TG to a mass spectrometer. I can connect a TG to a GCMS system. So I can even separate those gases and individually analyze and find out the mass spectrum of each. So these are all basically hyphenated systems wherein you are going to get different properties of the sample in a single sample in a single analysis. Okay. Now, what is the purpose of carrying out a thermal analysis? Most of you must be knowing this. I am just telling this basically for the students to remember what they've already learned. Characterization of materials. Using a thermal analysis system, a suitable thermal analysis system, you can many times you'll be able to characterize a material by looking at certain properties like melting temperature, melting characteristic of the material, crystallization characteristic of the material, glass transition. We are coming to that. What is glass transition? You all must be knowing because you are all polymer people. But I will tell you what is glass transition. We have few slides for that. And then sometimes decomposition. So all these changes, physical changes are going to give a lot of information as to what would be the characteristic of the material. Short-time evaluation of chemical reactions can be monitored, like evaporation, decomposition, sublimation, oxidation, reduction, and even cross-linking of polymeric materials. Then measurement of thermal characteristic values. Melting point, everyone knows, is a thermal characteristic of a material. Melting point, in fact, is a pointer to the purity of a material. A pure compound will have a very, very well-defined melting point. If there is going to be a variation, if there is going to be a deviation in the melting point, that shows either the sample is contaminated, sample is impure. So you get to know information about the purity of the sample by observing a very, very simple characteristic like melting point. Purity, softening temperature, expansion coefficient. So a lot of things you can gather by carrying out a suitable thermal analysis method. Now, thermal analysis methods, there are different techniques available. We'll be only discussing just 2 or 3 over today and tomorrow. And what is the parameter that is measured when you are going by a certain technique, and what is the parameter that we are able to measure, and what is the instrument that is used for the measurement of the system. We talk about thermogrammetry. in popular, it is written as TG, capital T and capital G. If you write capital T and small g, it becomes totally different. It will be, as everyone knows, it will be glass transition temperature. So here it is, capital T and capital G, thermogravimetry. And we are concerned with the parameter that is measured is mass, the change in mass. And the instrument that is employed is a very, very powerful and very, very sensitive thermobalance. That's the heart of the system, thermobalance. Tomorrow we'll see what type of balance we can use for this. Then derivative thermogravimetry, DTG, we are going to see the rate of change, a dm by dt. Again, we are going to use a thermobalance. Differential thermal analysis, DTA, what is being measured is Ts minus Tr, the difference in temperature between a sample and a reference material. That is why it is known as Ts minus Tr. Ts is the temperature of the sample and Tr is the temperature of the reference material. We are continuously monitor what is the difference between these two temperatures at all time. And we have a DT apparatus for that. We'll be using a thermocouple. Differential scanning calorimeter, DSC, dH by dt, that is the change in the heat content, the enthalpy content, change in enthalpy content. And that is what is going to be more important for us. I will consider that rather than DTA, DSC is going to give more information. I am not underestimating the power of DTA, no, never. But I am telling you, you will be getting a little more information when you go for a DSC analysis of a compound compared to DT analysis. So we have a DSC instrument for that. The instruments are fairly going to be same. You will see that. Then when we go to TMA, thermomechanical analysis, the parameter that is of importance is a deformation of the sample, changes in volume or changes in length. I mean, all this, and then we have got a TMA dialectrometer. Then we have got other things also, dynamic thermomechanometry, modulus and damping. There are so many instruments available for that. Evolved gas analysis, EGA, thermal conductivity. We have got EGA apparatus. Many times it can be achieved by even having a hyphenated system also. Then thermo-optometry, thermo-electrometry, thermo-osmometry. So where we are concerned with velocity and other things. So there are different types of, it's a very it's a large group of techniques coming under the common heading thermal analysis methods. Okay. So some of the most important, most widely used methods are, one is number one, DTA, differential thermal analyzer, DSC, thermal differential scanning calorimetry, TGA, thermogravimetric analyzer, and TMA, thermomechanical analyzer. That's why I've written all these four. But anyway, tomorrow we are not touching upon TMA. We'll be discussing only about DTA, DSC, and TGA today and tomorrow. We will not be discussing about TMA. Okay. What types of data you can get from thermal analysis? Crystal perfection, polymorphism. We'll discuss what is polymorphism going ahead. Melting temperature, sublimation, glass transition, dehydration, evaporation, pyrolysis, solid-solid interaction, purity, kinetic reaction, specific heat, a very important property. I mean, we are going to harp on this specific heat when we talk about MDSC. Such data are very extremely useful in the characterization of the material with respect to compatibility, with respect to stability, with respect to packaging and quality control. Many times, not only in polymer industry, when we talk about pharmaceutical formulations, compatibility is a very major concern. You are going to mix an active pharmaceutical ingredient and API along with a lot of excipients. There has to be proper compatibility, otherwise the formulation will have an extremely low shelf life. I mean, it will not be a proper formulation. It will not be stable formulation. So compatibility, either in polymeric material also it is there. I mean, many industries. I mean, so we are concerned with compatibility, stability of the formulation, packaging, and quality control. So a lot of important data can be available from the suitable thermal analysis system. Applications of thermal analysis. You can see the wide range of industries across which we have got plenty of applications. Perfumes and cosmetics, pharmaceutical industry, organic and inorganic chemicals, catalysts, building materials, glass, clays and minerals, fats and soaps, polymers and plastics, food industry, fiber, ink, pigment. I mean, you can see a wide list of compounds, industries or segments where we have got wonderful applications of thermal analysis. That's why I consider thermal analysis one of the major analytical technique which can be used across different industries. Now let us concentrate on DSC, differential scanning calorimeter. Now I hope the students know why we call it as differential, why we call it as scanning, and why we call it as calorimeter. So that I hope you all know. But I'm just giving, just refreshing what you have already learned, the definitions. When the moment you say calorimeter, it has something to do with the heat measurement. Everyone knows that. We have studied in basic college what is meant by what is a calorimeter and what is a calorimeter does. The calorimeter measures the heat that is going into a system, into a compound, into a sample, or coming out of the sample. Both can be measured. Either the heat that is going into or coming out of a sample can be measured by a calorimeter. Then, but when I say differential calorimeter, it measures the heat of a sample related to a reference. When you are trying to relate the heat of a sample with respect to a reference material, it becomes a differential system because you are trying to compare, you are trying to find the difference. That is why it's called a differential calorimeter. Now, we talk about differential scanning calorimeter. Differential scanning calorimeter does all the above and heat the sample with a linear temperature ramp. So when you talk about a differential scanning calorimeter, it is going to measure the heat that is going into the system or coming to the system, and is also going to compare the heat against a suitable reference material. And at the same time, it is also going to employ a linear temperature ramping for the sample because we are going to heat the sample and we need to optimize what is the heating rate, but it is going to be linear heating. And the ramping and the rate of heating, we need to optimize from sample to sample. Okay. Endothermic heat flows. Endothermic means heat is flowing into the sample. Exothermic means heat is flowing out of the sample. Whenever a sample is absorbing heat, it is a endothermic system or an endothermic change. Or whenever the sample is giving out heat, it becomes an exothermic reaction or an exothermic change. Okay. The same thing is repeated, differential scanning calorimeter. Differential means measures difference in temperature between the reference substance and the sample as a function of time in a specified atmosphere. This is what we have seen in the first slide. Scanning means measurement is carried out continuously in a programmable temperature range. You are going to heat the sample from a lower temperature to a higher temperature in a linear fashion using a certain specified means you have to optimize a certain rate of heating because I have the freedom to utilize or use different rate of heating. That's called ramping. But you have to optimize what is the ramping suitable for your analysis. Okay. And calorimetric means the temperature difference delta T. Here also we are going to continuously monitor the difference between the temperature of the sample and the reference material. And the temperature difference delta T is proportional to the changes in the calorimetric state of the sample. When I say calorimetric state of the sample, it is basically energy in the form of heat. And the resulting signal, whatever signal we are going to get from the DSC, is always expressed as milliwatt because it is the measurement of heat content, milliwatt. So that is a major difference between our DTA and DSC. In DTA, it is always millivolt, and in the case of DSC, it is always milliwatt. So please remember that. Now, DSC is a very important analytical tool because all transitions, when I said transition, the changes, all transitions, changes in the physical properties involve heat flow. Whenever there is a change in a certain property, there is a certain heat that is involved, heat flow that is involved. Without a heat flow involvement, no change can take place. Now, heat flow is always the result of a temperature difference between two objects. You have two objects, one is your sample and one is your reference. And there is going to be if at all there is going to be a heat flow, and that is a result of there is a temperature difference between the sample and the reference material. And because of the temperature difference, ultimately it results in a heat flow. In differential scanning calorimetry, the difference in heat flow between a sample and the inert reference material is measured at all time. The simple equation is delta Q is equal to delta T divided by R, where delta Q is the difference in the heat flow between the sample and the reference material. Delta T is the difference in temperature between these two, and R is the thermal resistance of the system. Now, this normally this is what you get. I mean, the principle of DSC, you have a sample and a reference. Okay, you are going to take a small amount of sample and a small amount of reference material in a furnace, and then you start heating. You have to decide from what temperature to what temperature you're going to heat. So the starting temperature and the final temperature, and what is the ramping, what is the rate of heat that you are going to utilize. And here you can see two different lines. One is a green line, one is a blue line. The green line represents your inert reference material, which is a highly thermally stable material. Nothing will happen in the working range of the instrument. No change will take place in the reference material because it is an absolutely thermally stable material. No change will take place. We are having those type of reference material. Okay. Now the blue line represents your sample, and both are kept in the same furnace, and we are going to start simultaneously. We are going to start heating, and as the temperature increases, both the temperatures are steadily going up simultaneously, going together. And at one point of time, you can see the blue line, it becomes flat for some time. It is not going up, it becomes flat for certain time. That means some change is taking place at that temperature. So till that change is completed, the temperature will not rise. And once the change is completed, again you can see the line is again increasing, the blue line is again going up along with the reference material. So when the curve has become flat for a certain period of time, at certain temperature, I mean, some change was taking place, and it can be different types of changes. It can be a melting of the material. Okay, it can be melting. So what is shown here is a melting peak. So that means there is a change in the heat flow. There is a transition that is taking place in the sample, and this transition can be either an endothermic transition or an exothermic transition. Both are possible. For example, here what is shown is a melting of the material. So melting is always an endothermic transition. That means heat is taken by the sample so that it can melt. And melting an endothermic transition in our system is always shown as a downward arrow in the negative direction. Whenever there is an arrow in the positive direction, it stands for a exothermic transition. Okay, now you can see the melting peak, and once the melting is completed, again the temperature is going to rise. Okay, so that is how we find out what is the type of transition that is going to take place, and depending upon the transition changes and depending upon the curve that we are going to get, we can understand whether it is an exothermic reaction, exothermic transition, or an endothermic transition. There are only two types of DSC curve. And same is the case with DT also. Tomorrow we'll see. There are only two types of DSC curves you can expect. One is an endothermic peak. That means the system is absorbing heat. And the second one is an exothermic peak, which is the system is releasing heat. Okay. So whenever there is an exothermic peak, you can see the peak is upward peak. You are getting an upward peak. And whenever there is an endothermic peak, you are always getting a downward peak. Okay. But that can also depend upon the manufacturer to manufacturer. Can be some manufacturers can give opposite also. At least in our system, an endothermic peak is always the downward direction, and an exothermic peak is always in the upward direction. So these are the two types of changes, two types of curves we can expect in a DSC analysis. Okay. Now, what can be measured with DSC? Qualitative analysis, fingerprinting of minerals, fingerprinting of clays, polymers. I mean, I'm just giving certain examples. So, fingerprinting of materials can be done. Sample purity, melting point. We also have a optional software, purity software, which is you can find out what is the molar purity of a compound. For example, I am giving tomorrow a chemical compound I'm going to give you. I want to find out what is the percentage purity of the material, whether it is 99.5% pure or 99.8% pure. Probably you can do the analysis, you can find out the purity of the sample with an HPLC system. But imagine HPLC system, how much time you are going to take. There's a column involved, there's a mobile phase preparation, the optimization process, how much time you are going to take, and a lot of solvents, usage of solvents, wastage of solvents, a lot of things are there. At the same time, if I have a purity software, without all these hassles, I can find out what is the molar purity of the material. So there is a purity software, you can find out purity. We can find out heat capacity, that is CP, heat capacity is very important. We'll discuss about that. Glass transition temperature, TG, I told you capital T and small g, that is glass transition temperature, crystallization temperature, TC, and even phase diagrams. So DSC thermogram, if you look at a DSC thermogram, whatever is the output you are getting from a thermal analyzer is called a thermogram. Like a chromatogram that is coming from a chromatograph, you are getting a thermogram from a thermal analysis system. So whenever there is a glass transition that is taking place in the sample, don't expect any peak. There will not be any peak. No endothermic peak, no exothermic peak. So whenever there is a glass transition temperature involved in the material, there is only a step you can exert. There is a baseline shift. That is what is shown on the extreme left-hand side, glass transition. Initially, it was coming flat, then suddenly there is a dip in the baseline, and again it becomes flat. So there is a change in the shift in the baseline, and that actually indicates the sample has undergone a glass transition. And then after that, there is a, you can see a positive peak that shows crystallization, because crystallization is always an exothermic reaction, so it will always provide a positive peak. Melting, melting is an endothermic reaction, endothermic process. So it is going to give a downward peak. And cross-linking, curing of polymers, suppose you have base and a hardener and all. Cross-linking is always an exothermic reaction. You can expect a positive direction peak. And oxidation also, sometimes you can oxidation, you can get a positive peak. So these are different, depending upon the type of transition that is going to take place in the sample, you can expect multiple peaks in the thermogram, thermogram of the compound. And if there is a glass transition involved, you can also see a step in the baseline. Okay, sorry. Now, what is the glass transition temperature? PG is especially for polymeric people, it's a very, very important parameter. In other industry, it may not be that important, but even in pharmaceutical industry, I can tell you, TG is not a very important parameter, but we have done an experiment for an API for a pharmaceutical company. There was a TG involved in the crystal of a pharmaceutical drug, and we had to do an exercise at subambient temperature, because the TG was somewhere around -20 or -15 or something. There was a TG involved, but normally TG is not a very major concern or major parameter in pharmaceutical industry, but in polymeric industry, polymers, glass transition temperature is an extremely important characteristic, because it has got an effect on various properties of the material. Step in the thermogram. That's why I told you there is no peak. Don't expect any peak, only a step in the thermogram. Step in the baseline. Transition from glassy and brittle state to viscous and rubbery state. So that is a transition. The material is getting transition from a glassy and brittle state to viscous and rubbery state. Observed in glassy solids like polymeric materials, And TG is termed as the glass transition temperature. So you can see the thermogram also when there is a clear-cut shift in the baseline, and we can precisely measure at what temperature this happens using the software, and so we can characterize the TG of the material, and we can measure. So glass transition temperature is the temperature at which higher molecular weight materials like polymeric materials transform from glassy state to a viscous and rubbery state. Simple definition. That's a glass transition. So you can see below the glass transition temperature, the material is in a glassy state, brittle state, and above the glass transition temperature, it goes into a rubbery state and viscous and rubbery state. So the change at which this is happening, that is the glass transition temperature, and this can be measured very, very precisely using a thermal equipment. Similarly, we can measure crystallization temperature TC, very sharp positive peak, because crystallization, as I told you, it is a exothermic reaction, disordered to ordered transition. Crystallization, the sample is going to be crystallized. So there is a changeover from a disordered form to an ordered form. That's why we say it is a disordered to ordered transition. Material can crystallize, observed in glassy solids like polymers, and TC is termed as the crystallization temperature. So here also we can precisely find out what is the crystallization temperature. Similarly, melting. Melting is a negative peak because now it's an exothermic, it's an endothermic transition. And it is the reverse of crystallization, ordered form to disordered transition. That's melting. So melting is the transition from ordered state to disordered state, and TM is the melting temperature. Okay. And melting happens to crystalline polymers, and glassing happens to amorphous polymers. Okay, crystalline polymers, they have got a very, very, very sharp melting point. So we can measure that. So melting happens to crystalline material and glassing happens to amorphous material. There are three types of DSC. Number one is heat flux DSC. Second one is called power compensation type DSC. And the third one, we'll very briefly see modulated DSC, temperature modulated DSC is called MDSC. So let us see what is meant by heat flux type and what is the difference between heat flux type and power compensation type. Okay. Now heat flux type, a sample and a reference material are placed on a metal plate connected to a furnace. The temperature difference of the sample and reference substance is measured. Heat can be measured since it is proportional to temperature. So that means we have a common furnace. You can see we have written TS and TR. TR is the reference material, TS is the sample material. Both are kept in the same furnace, and we have got a common heater for the entire furnace. There is a single common heater for this. So simultaneously, your reference material and sample is going to be heated. At any point of time, we are monitoring the difference in temperature delta T, which is equal to TS minus TR. So we are going to monitor the difference in temperature between the standard and the sample at any point of time using a thermocouple. But so it's a common heater. So please keep in mind it's a common heater. It's a common furnace, a single furnace with a common heater for the sample and the reference material. Now when we talk about power compensation type, we are going to have two different furnaces, one for reference and one for sample. It is not a common furnace. It is going to be two distinctly different furnaces we are going to have. And there will be individual heaters, not a common heater like heat flux, and individual heaters. But then why it is called power compensation? Now what happens when you are heating a reference material and a sample in two different furnaces, having two different heaters, and we try to, in the case of heat flux, we are trying to see what is the difference in the temperatures of these two, reference and sample. But here in power compensation, what we are trying to see, we will maintain the temperature of both reference and sample at all time at the same level. So suppose if there is some change that is taking place in the sample side, And then there is going to be, suppose if there is going to be a difference in the temperature, we compensate for the difference in temperature by supplying power. And that is why it is known as power compensation. We are going to compensate with the power so that the temperature difference becomes again zero. That means both the temperatures at all point of time will be maintained at zero level, either by supplying power to the sample side or to the reference side. That means we are compensating for the difference with the help of power. Power is supplied and compensated so that the difference is nullified and it is kept at the same level. That is why it is known as power compensation type. What we are giving, Shimatsu is giving heat flux type, but now majority of the people, majority of the manufacturers are changing over to or have changed over to heat flux type. And there are some, at least one manufacturer who was still or is still giving a power compensation type of DSC. And what is the difference between if you compare a heat flux type and a power compensation type? Most DSCs are a heat flux type today. Today, whatever most of the DSCs, what you are finding in the market, they are all heat flux type. Generally, heat flux type is more sensitive, more stable. Two very, very important advantage, very sensitive. Even a very, very small thermal change, thermal transition can be comfortably and sensitively measured by heat flux type. That's why it will become more sensitive and more stable. Power compensation, I am not telling it is bad. Power compensation type has faster response time and higher heating rate can be used as the furnace is smaller because individual furnace. However, this is not a major advantage. This function is only necessary in certain applications such as kinetic studies. Otherwise, this is not a major advantage. So there are people who are offering, there is at least one manufacturer who is offering a power compensation type, but most of the manufacturers are offering a heat flux type because it is more stable and more sensitive. And what type of chemical reactions can be monitored by DSC? I mean, there are a lot of reactions. I have given some few reactions, and these can be classified into either endothermic or exothermic. For example, chemical sorption, dissolution, dehydration, decomposition, oxidative degradation, polymerization, combustion. I mean, these are, and all these reactions can be either classified as an endothermic or an exothermic reaction. For example, combustion. Combustion is always exothermic because a lot of heat is given out. Dehydration, removal of water by heating is always endothermic. So it is, so that is coming as an endothermic reaction. Decomposition. The sample is absorbing heat so that it gets decomposed, endothermic reaction. So all the changes, all the types of reactions we are talking about can be classified into either an endothermic type or an exothermic. Similarly, we can study also set of physical reactions like crystalline transition, fusion, crystallization, vaporization, sublimation, desorption, glass transition. So all these again can be classified into endothermic and exothermic. Only thing you look at the glass transition. Glass transition, there is no peak. No peak is observed, only change in the baseline. I told you glass transition will be observed as a change in the baseline. There is no exothermic or endothermic peak for glass transition. Now we should understand what are the limitations of DSC. Okay. Now, naturally, there are couple of limitations that I just jotted down. We'll quickly go through that. Natural limitations of DSC, it is not possible to optimize both sensitivity and resolution in a single DSC experiment because both cannot be optimized at a time. Sensitivity, either you can optimize sensitivity, increase the sensitivity, or you can increase the resolution. Both cannot be optimized or maximized at the same time. Sensitivity is increased by increasing weight or heating rate. Okay, if you increase the weight, your sensitivity can be, of course, the signal will be more, sensitivity can be more, or even by heating rate. But what happens when you increase the sample size or you increase the heating rate, you may get sensitivity. Your sensitivity may improve, But problem is your resolution will decrease. So you are maximizing one at the cost of another. So resolution will become poor. At the same time, sensitivity will become more. So you cannot, the one limitation is both cannot be maximized at the same time. But when you go for a modulated DSC system, it solves this problem because it has two heating rates. In the case of normal DSC, we have got a single heating rate, it's a linear heating rate. But in the case of MDSC, we have two heating rates. One is an average heating rate, and second one is a modulated heating rate. Let's see what is that modulated heating rate. So average heating rate can be slow, so that improves resolution, and modulated heating rate can be high to improve sensitivity. So that is how we increase the sensitivity and resolution at a time in a single experiment in MDSC by using two different heating rates. One is an average one and one is a modulated one. Now, second limitation of normal DSC, baseline curvature and drift limit the sensitivity of DSC for detecting some of the very weak transitions. Some of the weak transitions, it may be difficult because there can be some baseline deviations or drift, and that will limit the sensitivity of detection. But MDSC can come over that. MDSC eliminates baseline curvature and drift in the heat capacity and reversing signals by using ratio of two measured signals rather than the absolute heat flow measurement by a DSC. We'll understand when I come to the MDSC side. And another limitation of DSC is transitions are often difficult to interpret because DSC can only measure the sum of the heat flow with the calorimeter. What is the actual total heat flow that is occurring in the calorimeter? That only can be measured by DSC. But in fact, the total heat flow can be divided into two different components, which cannot be done in normal DSC, but it can be done in MDSC. So MDSC minimizes this problem by providing not only the total heat flow, but also the heat capacity and the kinetic component of it. The total heat flow can be divided into two different components, reversing and non-reversing. So that is possible only when you go for a MDSC system. But a normal DSC will measure the total heat flow that is happening in the calorimeter. Okay. It's often difficult to accurately measure the crystallinity of a polymeric material by DSC because the crystallinity increases as the sample is being heated in the DSC cell. To measure the correct crystallinity of a material requires the ability to two different capabilities. One is it should be able to determine the true heat capacity. That means there is no transition. That's a base, true heat capacity baseline without any transition. Okay, and second one is quantitatively measure how much crystallinity developed during the heating process. A normal DSC cannot do that. So that is why we go for a modulated one. Complex data with transitions and reactions superimposed cannot be resolved in a normal DSC. When reactions are superimposed, suppose some changes are taking place when they are superimposed, such as, for example, glass transition and enthalpy relaxation. I am not going into what is enthalpy. I hope the students know, but this will be out of scope of this discussion. There are two terms you should understand: what is enthalpy recovery and what is enthalpy relaxation. And if anybody wants to know more about this, you can get back to me. I can give you a lot of information, but here we'll not be able to discuss because of our time constraint. So when reactions are superimposed, such as glass transition and enthalpy relaxation, they cannot be separated by a normal DSC, but a modulated system can do that. Okay, you can see that below the two different graphs. One is a total normal DSC measurement. Glass transition plus enthalpy relaxation, you get a single curve. But when you go for a modulated system, you can bifurcate, you can divide, you can separate it into two different components. One is a glass transition and one is a enthalpy relaxation. You can get two different signals. You can separate these two from the total heat flow. So that's the advantage of going for MDSC. Okay, we'll briefly go through. I'll not spend too much of time. I'll just briefly go through. And if anybody is interested in knowing more about MDSC, you can contact me. We can discuss it separately. But here it may not be possible for me to discuss too much of modulated system. Modulated DSC theory, MDSC uses two simultaneous heating rates. I told you one is a linear heating rate, that is what we normally use in a DSC, and we also have a modulated heating rate. Okay. Average heating rate. So MDSC, we have got two different heating rates. One is called the average heating rate. This gives the total heat flow data, which is equivalent to the standard DSC. So in standard DSC, what we are having is the average heating rate, which we normally call it as linear heating rate. That's the only heating rate that we normally use in DSC. Okay. And that gives the total heat flow data of the sample when it undergoes certain types of transitions. But when you go for a modulated heating rate, purpose is to obtain heat capacity information at the same time as heat flow. You will be able to get the total heat flow, and you also will be able to find out heat capacity information about the sample. It's very important. Heat capacity information is very, very important. And I hope all the students know what is the difference between heat capacity and specific heat capacity. Others, you please refer. Even this is the important terms. So what does MDSC measure? MDSC separates the total heat flow of DSC. Total heat flow is what we normally get in a normal DSC. And we are going to separate it into two different components. One based on the heat flow that does and does not respond to a changing heat rate, in the heating rate. Suppose some of the heat flows will not respond to a changing heating rate. Heating rate means our ramping. It will not respond to that. But some of the heat flow will respond to that. So there are two components. One type of heat flow will respond to a changing heating rate, and one type of heat flow will not respond to changing heating rate. And we are going to separate these two in a MDSC mechanism, whereas it's not possible in the case of a normal DSC. So MDSC applies a changing heating rate on top of a linear heating rate in order to measure the heat flow that responds to the changing heating rate. So normal heating rate, what is in a normal DSC, that is going to be there in MDSC also. Over that, we are going to superimpose a changing heating rate, a modular heating rate, and that will respond to the changing heating rate. In general, only heat capacity and melting respond to the changing heating rate. So you can see only two different transitions. One is a heat capacity measurement, and one is a melting of the material will respond to changing heating rate. Others will not. So that the reversing, and so there are two types of signals you can get from MDSC, reversing signal and non-reversing signal. And both signals are available in MDSC. So the reversing and non-reversing signals that will be available from the MDSC should never be interpreted as the measurement of reversible or non-reversible properties of the material. So in nutshell, modulated DSC benefits increased sensitivity for detecting weak transitions. All these types, sometimes these weak transitions may not be able to be measured in a normal DSC, but we can conveniently and comfortably and sensitively we can measure using an MDSC technique. Eliminates baseline curvature and drift. Increase resolution, we can get wonderful resolution without loss of sensitivity. So you are able to maximize sensitivity as well as resolution together, which is not possible in a normal DSC. Ability to separate complex thermal events and transitions into their heat capacity and their kinetic components. The ability to measure heat capacity, the structure changes during reactions and under isothermal conditions. Separation of overlapping transitions. We have seen an example, TG and enthalpy relaxation. In normal DSC, you'll get a single curve because it is an overlapping transition. But when you are using a MDSC, you can bifurcate it and you can get two different signals, one for TG and one for enthalpy relaxation. And direct measurement of heat capacity. Heat capacity also can be measured by DSC, but it is difficult. You have to carry out 3 different experiments to find out the heat capacity of a compound using normal DSC. But in MDSC, you can just in one analysis, one experiment, you can find out directly with a very maximum efficiency, you can find out what is the heat capacity of the compound. And only downside of the technique is it is a slow mechanism, slow data collection. That's the only downside of this. Modulated DSC reverse. There are two types of reversible transitions. One is called glass transition and one is melting. Both are reversible transitions. And there are non-reversible transitions. They are more crystallization, curing, oxidation, degradation, evaporation. These are all examples of non-reversible transitions. So transitions can be classified into reversible type and non-reversible type. And reversible type, we have only two: glass transition and melting, and the rest of things will be coming under non-reversible type. So this is how we can just see. I mean, let us not go too much of detail into this. Average and modulated temperature. We can see a green line and a blue line which is oscillating, like a sinusoidal oscillation. That's a modulated temperature. And the green line is a straight line. That's the average temperature. We can call it as a linear temperature change. That is what we normally apply in a DSC. And over that, you can see one blue line going up and down, up and down, up and down. That's called a modulated temperature. And this modulated temperature is overlapped on your linear temperature change. And then so that you get a lot of information which may not be coming from a normal DSC experiment. And modulate, this particular experiment, we modulated plus minus 0.42 degrees centigrade every 40 seconds. That means there is a normal the normal ramping is 4 degrees centigrade per minute. We are starting from, say, 40 degree or 30 degree, maybe room temperature. We are going to 290 degrees centigrade. That's the maximum temperature. And our normal average, that is linear rate, is 4 degrees centigrade per minute. That's our heating rate. That's our ramping rate. But what we are doing, every 40 seconds, we are changing this ramping plus minus 0.42. Either it will be 4 plus 0.42, next moment, after some time, after 40 seconds, it will be 4 minus 0.42. So you are having a modulation plus minus 0.42 over your 4 degrees centigrade, which is the normal rate. And this modulation is happening in 40 seconds. This is just one experiment. You can change the second, what is the period. Instead of 40 seconds, you can change it. Similarly, what is your modulation rate, that also you can change it. This is just an experiment. I can just show you. This is a modulation at the rate of plus minus 0.42. Every 40 seconds, that is the period. That's a modulation period. And your normal ramping is 4 degrees centigrade per minute, starting from, say, room temperature to 290 degrees centigrade. Okay. The same thing, a little expanded. And this is the period, you can say return period. I told you 40 seconds we are changing the temperature, rate of heating, modulated rate of heating. And that period can be optimized. It need not be always 40 seconds. Sometimes it can be 60 seconds, it can be 40 seconds. Sometimes it can be even less than that. So that is to be optimized by the user. So that period, not that heating rate is never done. So you can adjust the heating rate, average heating rate, and the modulated heating rate, and what is the period of modulation required for your analysis or sample application. So that is to be optimized by the user. So this is the modulated DSC. There is just one look at this. Don't let us not go deep into this. MDSC, heat flow, and signals. I told you every total heat flow is dH by dt is the total heat flow, and this is what we are getting from your normal DSC. And that is bifurcated into reversing Cp into dt by dt plus function of TNT, that is non-reversing type. You'll understand what are those. So this is the basic equation. Just have a look and just forget at the moment. dH by dt is the heating rate. Cp is the sample heat capacity. dt by dt is what is dt by dt? dH by dt is the total heat flow signal. That is what you normally get from a DSC, dH by dt, heat flow signal. And that is equal to, so your total heat flow signal, dH by dt, is equal to Cp multiplied by, where Cp is the sample heat capacity, multiplied by dt by dt. dt by dt is your normal heating rate, plus function of TNT. Function of TNT is heat flow, that is a function of time at an absolute temperature. So this is a basic equation of MDSC functioning. MDSC separates the total heat flow signal of DSC into two parts. And one is called a reversing part and one is called a non-reversing part. Okay, so same equation is rewritten here. dH by dt, total heat flow, is equal to Cp into dt by dt, which is the reversing part of the heat flow, reversing part. And a function of TNT is the non-reversing part. And reversing part, we have heat capacity, we have glass transition, and most of the melting process. And what is there in non-reversing? Enthalpy recovery, evaporation, crystallization, thermosetting curing polymers, protein denaturation, starch gelatinization, decomposition, and even some melting also can. So non-reversing part. So this bifurcation of the total heat flow is possible only by using a modulated system. Whereas in the case of normal DSC, you will only get the total dH by dt, that's a total heat flow. There is no bifurcation, everything is coming together. And how can you optimize MDSC experimental conditions? MDSC controls the heating rate applied to the sample through three experimental parameters. So three parameters are very important in MDSC. One is the average heating rate, that is so many degrees centigrade per minute. That is what we normally apply in that is the linear heating rate. Normally some 5 degrees centigrade per minute or whatever it is. That you have to optimize. Temperature modulation, amplitude. I told you, I have shown you some plus minus 0.42 in an expense. So you can change it. You can say plus, normally it is a change between plus minus 0.1 to 2 degrees centigrade per minute. That is your modulation amplitude. And then the third important thing is the modulation period. I had shown you the 40 seconds, but you can change it between 40 or sometimes you have 30 seconds to 100 seconds. So modulation period you have to optimize, modulation amplitude you have to optimize, and your normal average heating rate, linear heating rate, which normally do in a DSC, that you have to optimize. All the three things you have to optimize to get a very good MDSC experiment. Summary, MDSC is a very slow technique. Always start the analysis of a new material with standard DSC and use MDSC only if required. Don't go into MDSC all of a sudden. Go for a normal, do a normal DSC, and if required, only go for an MDSC system. If you want improved sensitivity, if you want better resolution, which you are lacking in a normal DSC, separation of overlapping transitions, and most accurate measurement of polymer crystallinity. Then you can go for MD. Otherwise, you can go for, most of the time, you can go for normal DSC. Optimum results require selection of optimum experimental conditions. That's a thumb rule. Now, some of the DSC applications, lot of samples, amino acids and proteins, amorphous material, biological materials, carbohydrates, pharmaceutical materials, polymeric materials, semiconductor. You can say a lot of list of things are there. And what type of results we can expect, what type of measurements we can do. So that is shown on the right hand side. And coming to some of the applications in pharmaceutical as well as polymer industry. And DSC application pharmaceutical industry, characterization, melting point, heat of fusion, specific heat capacity, water of crystallization, all these can be available. Purity, I told you, we have a separate purity software for that. You can find the molar purity. Polymorphism is very important in pharmaceutical industry because a drug can exist in different crystal forms, out of which only one crystal form is biologically active. Others are all inactive. And that is what is known as polymorphism. Polymorphism, the number one method to study polymorphism is X-ray crystallography. But you should have sufficient knowledge about X-ray crystallography to interpret the result. Second one is you can use an FTI along with a microscope. You can find out the polymorphism studies. You can carry out polymorphism studies. But the easiest method is DSC, differential scanning calorimetry. You will see an example. Then screening test of compatibility. I told you about compatibility, especially in formulations, and the stability test. See, heat characterization, melting point, heat of fusion, specific heat capacity are basic properties of compounds. And you can get all this information from a DSC analysis. And DSC method is faster and sample size is smaller. Normally, we require few milligrams of sample, that's all. These are melting peak, or you can say aspirin, salicylic acid acetate. And melting peak, you can see, it's an anti-inflammatory and anti-rheumatic, anticoagulant material. and you can see you can get a very sharp melting peak. And along with the melting peak, what is the heat content change? That also you can get from DSC. So here, what is the heat of melting? 177.8 joules per gram. This information you not get from DTA. DTA will give you a melting peak. That also will show you 135.6 degrees is the melting point of aspirin. But what is the heat of that melting? That is not available in DTA. That will be available only in DSC. Okay. That's why DSC, I told you before, it gives more information. Purity studies, see, purity can, as I told you, purity can be available by SPLC analysis. For example, benzoic acid. If I want to find out the benzoic acid purity, I can do an LC analysis, but what is the time, all those. But here, if I got the purity software, hardly few minutes, I can get the purity. 99.51 is the percentage molar purity of my sample. I can find out using DSC. Okay, it's very simple. Polymorphism study, I told you what is polymorphism. X-ray diffraction is the number one method. FTR can be used and DSC also can be. And DSC is the easiest method. And in the case of DSC, the polymorph will show a separate melting peak. Sulfathiazole sulfur drug. It exhibits polymorphism. Now, if the material has got a polymorphs are normally found because of the manufacturing conditions and types of solvents you are using, chemicals you are using, different process conditions. Sometimes polymorph formation will take place. And if polymorph formation is taking place, the manufacturer will adjust and modify the processing conditions in such a way that polymorph formation is reduced to the minimum or practically nil. Because polymorph is of no use, it is biologically inactive. It is not going to act on the body of the patient. So it will be active form. Here we have got 202.2 degrees centigrade is the actual melting of a thiazole, sulfathiazole. At the same time, we have got two different polymers here. One is at 175.6 degree and one is 157.8 degree. And so we have got two different forms in this, and this can be clearly separated by a distinct peak. So every polymorph will provide you a distinct peak in this or DSC. That's why it becomes very easy for you to understand. It's very easy for you to study more polymorphism in pharmaceuticals as against a crystallography or FTIR. Screening test of compatibility, as I told you, formulation. It takes a lengthy study, but by using a certain programs, we have got certain screening programs also, mathematical programs, modeling. We can actually predict what is the screening and even what is the shelf life of the compound. These two things, suppose I'm mixing magnesium oxide and benzoic acid in the formulation. If they are compatible, there should not be any change. So for example, you can see benzoic acid got a very sharp melting peak at 123.32. Magnesium oxide is an inorganic oxide. It has absolutely no effect, the straight line. But when you are mixing benzoic acid and magnesium oxide, you can see the thermogram is totally changed. So that means that particular combination is a what you call is incompatible. Proper combination, probably you have to change the combination or change the ratios. Similarly, trimethoprim and polyvinyl pyrrolidone. Trimethoprim is an antibacterial material in pharmaceuticals, and polyvinyl pyrrolidone is a cross-linking material. Okay, and these two are mixed together. You can actually see what is the compatibility of this using a DSC experiment. We can use the topmost one, the green one is only PVP, second one is TMP, and then you are having a 75%, 25% mixture, physical mixture. That means they are compatible. But suppose if you grind this mixture, 75% of PVP and 25% of TMP, suppose if you grind it, the nature of the material is changed and the thermogram is changed. So that means that grinding has given some changes in the material, so it may become incompatible. So those type of studies in pharmaceutical industry are very, very important, and people are using DSC for those. Photovisual DSC, I think I am not spending too much of time on that. Here, when you are having a photovisual DSC, there is an attachment, visual monitoring of the changes that are taking place in the sample. You can see, you can actually view that, and with the CCD camera, you can even take a photograph of that. Okay. Measurement of margarine, this is a food application, how the food sample is melting, and actually what happens when the food material is undergoing melting. These things you can visually see using a microscopic type of attachment that is connected to the DSC. Okay, let us not spend too much of time. Measurement of sulfathiazole, again by photovisual DSC method. Heat denaturation of proteins by DSC. See, the protein structure plays a very important role in this function. The protein structure and its function are influenced by many factors, such as the solvent is one factor, the temperature, the pH of the solution, all these can affect the protein structure. One common method for analyzing the protein stability is by differential scanning calorimetry. When higher order structure of a protein is inversibly changed, it results in loss of activity due to degeneration. And this is referred to as thermal denaturation. Okay. And the result is an endothermic peak in DSC. Similarly, you can the pH dependence of denaturation temperature of lysozyme. So this can be studied. I am skipping all this because of the time constraint. Measurement of polymer blends by DSC. See, we have LDPE, pure LDPE, and we have pure polypropylene. And we are mixing polypropylene and LDPE in a certain combination, and using a partial area software, even we can quantify what is the LDPE content in the mixture, what is the PP content in the mixture. And we can actually find out from the melting, we can actually find out what is the heat of melting. We can even do quantification, but we require software for that. We call partial area software. Software is there. And with that, we can actually quantify the content of PP and LDPE in the polymer blend. Influence of heat treatment on polyethylene terephthalate, PET. A sample of PET bottle was measured by DSC. When the original sample, in the original sample, we are able to see a very clear melting peak at 254.8 degrees. And the sample was heated only once by a certain ramping, and we were able to observe a clear melting peak at 254.8 degrees. We showed that the structure before melting was crystalline. So we are sure the material was crystalline before it was melted. Now, after the sample was melted, it was rapidly cooled, and again it is reheated. We have cooled the sample very rapidly after the melting process, and it is again reheated. And during the reheating process, we are able to see a glass transition temperature at 77.6 degrees, which shows that PET becomes non-crystalline when it is cooled very rapidly. The effect of rapid cooling on the PET, it has become non-crystalline, and then hence it has displayed a TG at 77.6 degrees. So this can be seen in the reheating process and the thermogram. And finally, an exothermic peak is observed at 136.8 degrees, which shows that the non-crystalline PET changes to crystalline form at 136.8 degrees. So you can actually study the heating and rapid cooling and reheating process on a polymeric material, and you can get from the corresponding thermogram, you get a lot of information. So what is the TG after reheating, and what is the crystallization temperature, and what is the final melting? Final melting is again matching 254.8 degrees. So these are DSC curves of PET bottle, first heating and second heating after rapid cooling. Another important, we are coming to almost end of this thing. For polymeric people, a very, very important application, oxygen induction time, OIT. So let us examine oxygen induction time of polyethylene. Many times polyethylene is used for covering electric wires and cables. All these cables and underground cables, electrical insulation, we are using a polyethylene coating. So polyethylene sheets are covering the cables actually. Over a period of time, it absorbs atmospheric oxygen and deteriorates gradually because it absorbs oxygens and undergoes oxidation, and it undergoes deterioration. Now, to prevent the deterioration, when it is getting formulated, the cable industry, they'll be adding a lot of antioxidants to prevent this type of atmospheric oxidation of the material. but then antioxidants are added to the PE formulation to prevent this oxidation. But we do not know what is the effect of these antioxidants, whether they are effective, they are not effective, whether the change in antioxidant is required. All these studies can be done by DSC analysis. And this effect can be investigated by measuring. There is something called oxygen induction time, OIT, for a polymeric material. This can be done by DSC. What we normally do, the sample is heated in nitrogen is our normal atmosphere, nitrogen atmosphere to specified temperature. Okay, now you go to say 150 or 180, whatever temperature you are heating the sample under nitrogen blanket. And after reaching that temperature, you have already set a temperature, say 180. Once that temperature is set, you change the atmosphere from nitrogen to oxygen. We are going to introduce oxygen into the furnace at that particular temperature. So at 180 degree, we are introducing nitrogen, we are introducing oxygen instead of nitrogen, and then we continue heating, and the time from inducing oxygen to the beginning of the exothermic peak. So what happens when you start heating, again the sample will undergo oxidation at one point of time because of the effect of oxygen and effect of temperature. And whenever there is an oxidation taking place, you can expect a exothermic peak. So the moment you introduce oxygen, start counting your time. And then when the exothermic peak starts coming, up to that time, that is known as OIT. That is known as oxidation, oxygen induction time. And this oxygen induction time can depend upon what is the starting temperature. Instead of 180 degree, you change some other temperature, the OIT will change. So this time can change depending on the temperature at which the change over has taken place. I'll just show you two examples before I finish. Oxygen induction time of polyethylene. See, we are heated up to 190 degrees centigrade in presence of oxygen, in presence of nitrogen blanket. At exactly 190 degrees centigrade, we introduced oxygen in the system. In place of nitrogen, we introduced oxygen and continued heating. And then what happens? After around 78 minutes, 78.5 or something, 78 minutes, an exothermic peak starts coming out. That means it has started undergoing oxidation. So for this PE film to undergo oxidation, it has taken 78 minutes to undergo oxidation. And that is what is called the oxygen induction time. After inducing oxygen, how much time it has taken for the polymer to undergo oxidation. Now, if I change this time from 190 to 200, you see the drastic change. If I heat the sample originally to 200 degrees centigrade, and then I introduce oxygen, you see the OIT is reduced to 20 minutes instead of 78 minutes. So the OIT also depends upon what is the temperature you are introducing oxygen in place of nitrogen. So there can be, as I told you, there can be provisions for introducing different atmospheres. That was my starting point. If nothing is mentioned, nothing is suggested, then your experiments are always carried out in a blanket of nitrogen. That is 100% inert atmosphere. Okay. And I think that is my last slide. I'll request my colleague Rajesh to spend 5 minutes on this topic. Rajesh. Hello. Hello.
Hello, sir.
Rajesh is there? Rajesh?
Yeah, you're audible.
Rajesh is not there, madam.
I have seen him, but right now I'm not. No, I think he's not.
No, he is not there.
Oh, if Rajesh is not there, if there is any questions, we can take it up, Dr. Jishan.
Now the session is open for discussion. So if you have any doubt, you can unmute your phone and talk to Girijan sir directly, or if you have some technical issue, you can write in the chat box, then we can address to him.
I think probably students may find it a little a little dry topic as compared to chromatography and spectroscopy, as I told you before. But I think it's a very interesting topic. It's a very interesting technique, having wide applications in major industries, various areas. And we have a, I don't know whether Rajesh is there or not. Rajesh was supposed to be there. I'm not talking about the product, but we have a DSC which can work from minus 140 degrees to 600 degrees centigrade. Maximum it can go to 600 degrees, and minimum temperature that is possible is minus 140. We can get this minus 140 degrees by pouring liquid nitrogen into the system. So we can, some of the transitions, especially in polymers, we study some of the transitions at subambient temperature. Most of the time it is required in polymeric material. Where pharmaceutical applications, I have come across extremely 1 or 2 cases where we had to take the temperature to minus 20 or minus 30 degrees centigrade. Otherwise, most of the time it is well above room temperature. But in many times polymeric materials, we go below 0. So our instrument can go to minus 140 degrees centigrade to 600 degrees centigrade maximum. And this minus temperature also can be achieved by 2 different methods. Either you can pour liquid nitrogen. There is a built-in Dewar flask inside the equipment. You can pour liquid nitrogen manually also. Otherwise, there are 2 equipments, accessories, wherein there is another accessory wherein the liquid nitrogen can come into the system automatically through a valve. So that's also possible. And one more option is, if your minimum temperature is not below 50, minus 50 degrees centigrade, we also have a electronic cooling type. That's called a Peltier cooling system also. Thereby, we can avoid using liquid nitrogen, and we can go to minus 50, but we cannot go below that. Minus 50 with Peltier cooling. That's called an electronic cooling system, where you don't require liquid nitrogen. If you want to go below minus 50, if you want to go to minus 100, minus 120, then the only option is to go for liquid
nitrogen. Sir, here is one question. I will just read it for you.
Yeah.
Is that possible to measure pore size distribution using DSC?
Pore size distribution, no. Pore size distribution, we have got specific equipments coming. Okay. We have got pore size measurement equipments are coming. Okay. Not possible by DSC.
Okay, thank you. And there are no further questions. So okay. Thank you, sir, for a wonderful lecture. Now I request Dr. Saumini C, coordinator of this program, for vote of thanks. Saumini, please.
Good afternoon, all. It's my pleasant duty to propose a vote of thanks. On behalf of the PG and Research Department of Chemistry, MES KVM College, Valancheri, I express my sincere gratitude to Girijan sir, our chief guest, for sparing his valuable time with us in this evening. Girijan sir gave a wonderful talk on the topic, differential scanning calorimetry, starting from the basics of the technique to the advanced method like MDSC. Actually, this method is not aware to me. MDSC is not aware to me. And I am sure this session is very much useful to the students, researchers, and teaching community. Thank you, sir, for your wonderful session.
You're welcome. You're welcome.
Next, I thank our beloved principal, Dr. C. Rajesh, sir, who is the person behind all these type of activities in the college. Our sincere thanks and gratitude to you, sir, for inaugurating this session. Next, I would like to express my sincere gratitude to our eminent and loving HOD, KM Rukia teacher, for constantly supporting us to organize such interactive sessions. Thank you, teacher. I sincerely thank Dr. Preeti teacher for the welcome address. And I would like to thank all the teaching faculties of the department for giving valuable suggestions during the organization of this workshop. I also express my deep sense of gratitude to Dr. Jisha teacher and Jensi teacher for rendering their help during the conduct of this program. I would like to express my sincere thanks to all the teachers, research scholars, and students for effectively participating in this session. I also thank Mr. Abhilash and Shahul for rendering the technical support before and during this session. Once again, thank you all for your kind support and participation. Thank you, sir. Thank you.
So I'll meet you all tomorrow at the same time, 3:45 tomorrow.
Okay, thank you, sir.
Okay.
Participant, please fill the feedback form circulated in the chat box. Thank you all for participating. See you all tomorrow. Okay.
Okay.
Thank you. Bye.
For being with me whole afternoon, and I'll see you all tomorrow evening at the same time. And let us have another wonderful discussion on a different topic in thermal analysis. Okay. Okay. So bye bye. I am logging out. Okay. Bye. Thank you.
Okay.
Thank you, sir. Thank you.